My name is Alpern, and you might be asking yourself, hey, what are quantum mechanics and what are electron configurations? Well, I'm here to show you. The quantum mechanical model. Development of the model. Although other models were popular in the early 1900s, Schrödinger developed a more involved model that utilized quantum mechanics. In his model, a mathematical description of an electron's motion was given by 4 quantum numbers. The principal quantum number, n. The principal quantum number designates the main energy level or shell of an electron. The values of n range from 1 to 7 and they describe the size of the electron cloud. Increasing n number is increasing reactivity. Angular momentum quantum number, L. The angular momentum quantum number designates the sublevel of an electron, ultimately giving the shape of the orbital. Typically, when L equals 0, it's a sphere, and when L equals 1, it's a dumbbell, 2 double dumbbell, and 3 flower. Magnetic quantum number, ML. The magnetic quantum number designates the orbital where the electron is. ML tells of the axis and therefore the direction in space that the orbital takes. ML is completely dependent on L and its values range. Spin quantum number, S. The spin quantum number designates the spin of the electron and describes its behavior, not its location, either up or down. Once the 4 quantum numbers are known, the electron configuration is known. To write electrons' configurations, put the first quantum number next to the second quantum number in letter form, and then put a variation of the third and fourth quantum numbers in the exponent spot of the letter. Additionally, put the configurations of other elements previously at the beginning. For example, chlorine's electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p5.
Orbital diagrams. When drawing orbital diagrams, use flat lines or boxes to represent each orbital and represent electrons with up and down arrows. Off-ball principle, Hund's rule, and Pauli exclusion principle need to be followed. The off-ball principle.
Electrons enter the orbitals of lowest energy first. Hund's rule. One electron enters each orbital until all orbitals contain one electron with a parallel spin. Pauli exclusion principle. Only 2 electrons can occupy an orbital and they must have opposite spins.
Okay, so basically how you draw orbital diagrams, draw individual lines for each orbital. I did the valence shell of chlorine here, which is 3s and 3p. S only has 1 orbital, so there's 1 line. There are 2 electrons in S, so 1 upward spin, 1 downward spin. In P, there are 3 orbitals, so I drew 3 lines, and using off-ball's principle, start at the lowest orbital, so start here, draw this electron first, then continue, leaving 1 in each orbital, following Hund's rule, do 1 upward the next orbital and 1 upward the next orbital. Then you can return to the first orbital and do one of the opposite spin, which fulfills Pauli's exclusion principle since you use parallel spin in these other 2 orbitals. And then continue to fill with this maximum of 2 electrons in each orbital, and since you only have 5, because chlorine has 7 valence electrons, this one only has 1 electron in it, this orbital. So that's how you draw orbital diagrams. Congrats.
The AP exam will have many diagrams on quantum mechanics. For one, orbital diagrams, which we've already learned how to do. Another is recognizing orbital shape. In this case, it's a double dumbbell, so we know it's the d orbital. The AP exam could also ask why the axes change for the orbitals, and that is due to the change in the magnetic quantum number, ML. The exam could also ask you which scientist the model belongs to. In this case, this is the quantum mechanical model, so it belongs to Schrödinger. Time for some practice!
Okay, so for this first one, the energy level here is 3, so n equals 3. L equals 1 because P is equal to 1 as the L angular momentum quantum number. So translate that to 1. ML is 0 because it's the second orbital in the P domain, so you go 1, 2, and this is the 0, where this is negative 1, and this is positive 1. Then S is 1/2 because it's a positive spin upward in that second orbital, and 3s2 translates right here, and then 3p2, 1 electron there, 1 electron there, and empty orbital here. For the second one, n equals 4 because it goes up to the 4th energy level, and now remember, D's energy level is always n minus 1, so that's why the 3 is there. but L equals 2 because it is the angular momentum quantum number. L for D is always 2. ML is also equal to 2 because this is equal to -2, this is -1, 0, +1, and +2. And since there are 10 full electrons in that D domain, it is in the last orbital, where it's a downward spin, so S would equal -1. And this is a fully filled, stable configuration for zinc. And the first one is for silicon. So that's basically it. Congrats if you got that right.